Hello, ladies and gentlemen. I guess we see that we are back to talk about more about power supplies because some of y'all are not used to them, but in this field, you will have to. And the special guest is still the same man that you've seen before. He still is a myth. He still is a legend. And he's your favorite director of manufacturing technology. It is the future Dr. Don Wilson, but you can refer to him as Dr. D.
Hey everybody! Dr. D couldn't make it, so he told me to teach the class. And I think you know who I am. I'm Plank. So we're going to start with the discussion of...
We still got problems, Plank.
What's that? What's the problem?
Oh, we still have issues, Plank, but we ain't going to talk about it on the screen right here.
Issues. But anyway, today we're going to talk about power supplies.
Get out of the way, Plank. All right, so hope everyone's good. We're going to talk about power supplies in part 2. I have the notes from last time. So this is setting the stage for what we're going to talk about today. And what I want to do is, again, we're going to talk about voltage regulation and look at some actual power supplies that have voltage regulation. So last time I was talking about the pinout of a typical voltage regulator IC, and these are two of the most common ones that makers, or you'll see them in like 5 volt or 12 volt supplies. So you got the 7805, which is a 5 volt power supply, it's positive voltage regulator, and then we have a 7812, which is a 12 volt positive voltage regulator. They also have negative voltage regulators, but we're going to talk about positive voltage regulators. Okay, so one thing I want to clear up was about the package. And the package is basically how the device is put together. So this is a sketch that I showed last time. It's got a heat sink. That heat sinks allow this part to actually reach its maximum current values. Typically for a 7805, even for the 7812, I think it's like you can probably source up to like 5 amps. So that heat sink's going to help, and you put it on a heat sink. And if you don't know what a heat sink is, it's this guy right here. Okay. So there's actually a transistor in here too. And the ideal here is you put thermal paste on the tab, and then you affix this part onto the heat sink, and then with the thermal paste, it'll allow it to basically maintain the proper thermals where it won't like self-destruct, okay? Because transistors or integrated circuits, they can reach a point called thermal runaway, and that's where it's just sourcing too much current and it'll self-destruct. So this heat sink, and they come in different sizes, it allows the, in this case, is convection airflow. That's why you got these fins. The air is actually circling around it, and that's going to keep that device, in this case, there's a power transistor, from self-destructing. Likewise, the voltage regulator. Actually, you can see one down here too. That's a good example. Down there, you can see where there's a power transistor, and that is being managed in terms of the thermals based on the chassis here. Okay, and there's thermal paste, and that helps with the heat transfer. Okay, so that's the 7805. 7812 has a similar pinout. You can see here you got VN, that's where you put your voltage. The voltage has to be greater than what the IC is rated at. If not, what happens is it'll just pass that voltage to the output pin of the device. And of course you got ground. So if you look at symbols, and some of you who have me in previous classes always say that one of the key aspects to recognizing these physical parts is the symbol. The symbol, if you look at it very closely, it was designed so that you can recognize the voltage regulator. So you can see here, VN is on the left-hand side, and then your V out, that's the pin right here, is on the right-hand side, and in the middle is your ground pin. So this symbol, this electronic symbol, represents the package. So when you see it on circuit schematic diagram, you know exactly it's for a voltage regulator. Okay, so that's something to keep in mind too. And something to practice. Start looking at diagrams, meaning schematic diagrams, and really understanding what the relationship of these symbols are to the physical part, because it will help you to troubleshoot. And the first step in troubleshooting is being able to identify the components on the board and likewise on the schematic diagram. Okay, so now we're going to look at these two power supplies. They're both B&K, or BK power supplies. They're adjustable. And we have one, which you already seen, the inside, took it apart. But right here on this printed circuit board, and the wiring is very atrocious here. But
Tell them why it's so atrocious from your professional perspective.
well, I only thing I can think of is, you know, like cost. I mean, they don't have any wire management that's going on here. So the idea was to make a product as quickly as possible. BK is a good company, but apparently this wiring kind of, you know, they just said, hey, let's chip the product out. Yeah, there's better ways to do it. You can actually have connectors that's on the board. It'll make it more easy to remove the printed circuit board from the chassis here. So this is known as point-to-point wiring. So you have the power supply that's on the board here, but all these wires are directly going to other components, and therefore it's point-to-point, right, with the wiring. These are solid gauge wires. I think if I was going to do it, I would use more stranded wires so you have more flexibility. But I guess what they're trying to do is they want to make sure that this printed circuit board is intact on the chassis, and the solid wire will provide that. It's an attachment feature, right? Kind of give it rigidity. So if you're moving around, it won't be bouncing on the board. But there's effective ways to do it. But I think they did this wiring for cost purposes. But again, it's not the way that I would do it. Okay, but it works. Okay, BK has been around for a long time, still making products, and it works. But hopefully, their new power supplies don't look like a science fair project. Okay.
Did you really just say a science fair project?
It's a science fair project, man. Look at it. It's just, I mean, would you show this to a potential company you want to work for and say, hey, I built this power supply and your wiring management looks like that? No, I wouldn't do it. But yeah, it's a science fair project. So here we have the voltage regulator IC. Now, this IC looks different than what I've shown on the board here. And just to kind of put things in context, the 7805, 7812 is in a TO220 package, and that's this guy right here. So it looks like a transistor. This is a transistor, but to make that connection with the 7805, 7812, it's an integrated circuit because it does have transistors and diodes and other components. It may even have a few little resistors packaged in it. But it's really taking a discrete design. Like you can actually build a voltage regulator using transistors on a breadboard, or in this case a printed circuit board. But what they've done is to minimize the packaging, they put it into and this is a TO220 package, okay? So that's one way of manufacturing a voltage regulator. The other one is this guy right here, okay? And I'm gonna cheat here a little bit. That is it's an LM723 voltage regulator. It's National Semiconductor. And I'm trying to remember, somebody bought National Semiconductor.
Texas Instruments.
Texas Instrument, thank you. And you see a lot of buyouts. So when you pull data sheets, you know, you might see the previous manufacturer, but then a lot of mergers and buyouts occur. So Texas Instruments bought National Instruments. So that's part of their product portfolio. But this package right here,
National Semiconductor.
this is National Semiconductor, right?
Yeah, because National Instruments is its own company.
Oh, okay. National Instruments deals with virtual instrumentation. I'm sorry, it's Texas Instrument. That's what I wanted to say.
Yeah.
Okay, I'm blending my words here. Maybe I need to get Plank to do the discussion here. What do you guys think?
I want to do it. I want to do it. I
No,
wanna do it.
no.
Okay.
I asked Don, not Plank.
Okay.
You don't pay me enough, Plank.
Hey, watch it.
Uh-huh.
All right.
Remember what happened the last time, Plank?
We're not gonna get into that.
Then you better know your role.
So this is a dual line package for the LM723 voltage regulator. Dual line means that if you notice, it's got pins on both sides. So that's what a dual line package is. It's a DIP, as they call it. DIP, dual line package. So this particular IC is unique compared to the 7805 or the 7812 because those are known as fixed voltage regulators. This particular IC is an adjustable voltage regulator, meaning that you have the ability to adjust from these banana jacks a range of voltages, which gives you more flexibility. So when they were looking at, meaning BK, the aspect of wanting to create a power supply, they wanted flexibility, and therefore they selected this particular package because it has adjustability. Okay, so that's that particular package. So you got DIPs and you got the TO220 package. Also, they actually have surface mount. So like your smartphones, they have voltage regulators in there. The chargers, because everything's getting real thin and small, they have surface mount, and they use various packages for that. So this one particular product does have a surface mount version of it, and you can really make this design smaller. Actually, these capacitors here, you can actually select surface mount components along with this transistor, even the resistors. Okay, so everything on this board can be surface mount, and it'll make it smaller. But again, we're talking about the time frame when this was developed, and this is probably maybe 70s, 80s technology, which is still good. So it still works.
Yeah.
Okay.
All right, Don. We got in this part right here for part 1, and we'll be back for part 2. Part 2. Dr. D, please continue.
He's not gonna do this part. I'm gonna talk about data sheets and data.
Get out of here, Plank. You don't know what you're talking about. Okay.
Plank, I'm going to put you in the machine shop. We know what happened last
He's
time.
always trying to steal people's thunder.
Hold on, wait a minute. Plank, remember the last time you tried to get on my nerve? What you mean? Remember what's on the top of your head? Yeah, know your role.
I got a brain on top of my head. I don't know what you're talking about, brother.
Yeah, what's the brain covering up?
It's trying to keep that knowledge in.
And what knowledge starts with? What letter does it start with?
Hey, man, I don't know what you're talking about. All I know is I want to talk about data sheets. Can I talk about this data sheet here for that integrated circuit?
Don can, you can't. Know your role.
All right, so data sheets. Probably you have not been exposed to data sheets. Here's the data sheet for that integrated circuit that's on the printed circuit board, or PCB as they call it. And what the data sheet has in terms of information is, it shows, well, you can see here the connection diagram, so it talks about the various packages. This is the DIP package representation I was talking about, and it shows the pinout, meaning the numbers, and then it actually has the description of the pins. Okay, here is the equivalent circuit. So this is showing like an inside view of this package and its various components. So here's a symbol for an amplifier, and then here's a symbol for another amplifier, but this is a inverting amplifier, and it has the pinouts that you see right here. So depending on the application that you're using, this op amp, and it's called an operational amplifier, it has integrated components in it as well. You can actually build an operational amplifier, but the complexity is probably will take as much space as what you see here. Therefore, they put it all inside of this DIP package, okay, to save space. And here's the surface mount that I was talking about package. Now, even though it looks kind of big here, but if you actually saw it on the board, it's really small. So one thing I encourage you folks to do is if you have some discarded electronics, start exploring what those components are. You have an understanding of symbols, or reinforce the symbols, meaning you can draw the symbols, and understand, you know, how these products are made, because everything is getting smaller, and therefore if you're going into the field, meaning automation controls, or you're doing troubleshooting, all this information is important. That's where the data sheet comes in. It gives you a convenience of having everything that you need. It talks about the description, gives you features, some of them which we'll see in a minute. Talk about applications, how you can actually use the product in various applications, okay? So this next sheet is really critical because it gives you the, as you can see, the absolute maximum rating. So again, if you're replacing that voltage regulator and for some reason you cannot find it, say at Jameco Electronics or maybe Element 14, but you can DigiKey, you can cross-reference, and the cross-referencing is based on knowing what these ratings are. So you can see the maximum rating here, and this is related to when they do testing. So they, in this case, they had a pulse voltage, and it went from plus to minus V, and it's got, they kept the pulse there for 50 milliseconds, and it's at 50 volts. And that's important because a lot of times these products, especially in an industrial environment or in a laboratory setting, if you're using it as a test equipment, you want to really push that product you're testing to the limit. Therefore, the test gear has to have a certain limit too, right? Maximum. So that's what you see here. It's got the continuous voltage, so it's from plus to minus V, so they went from minus to plus in terms of voltage range, and it's 40 volts. So you can run this guy, have it set for 40 volts maximum, and you'll run continuously, and it should provide regulation, okay? You can see here about the input-output voltage differential. So this is pretty cool because the makeup of these integrated circuit amplifiers, they have a differential stage. And the differential stage, and this is a really good example of that, is this op amp right here. That's what an op amp really has. It has a differential stage because you can actually have a negative signal go in, or you can actually have a positive signal, and that will affect how this amplifier will do its amplification. So that's, in this case, they're saying the high, the input-output voltage differential is 40 volts. So that's what they put into this chip right here, the plus or minus on these pins, and they noticed that 40 volts was the maximum that this chip can handle. And the maximum could be related to the thermal aspect. Like a lot of times I'll put my hand over an integrated circuit and just keep it on that component, and if it has a, you know, a nice warm feel to it, great. But if it's one where if I put my hand on it and I have to move it quickly, that means I'm exceeding this maximum rating, whatever the rating is. It could be more current that's sourcing through it or supply voltage, okay? So that's something to be cognizant of when you look in this area, what is the maximum ratings? Now, the electrical characteristics, this really deals with, there's test conditions, so you can see in this column when they actually looked at these particular parameters, this is line regulation. So they actually built a little test circuit, and it could actually be on a little breadboard. And they put in these various conditions, and then from there they measure what the outputs or the responses are based on these conditions. So it's always a min. Typical is basically, I call it the nominal value, and that's where, like, if you're going to go to like DigiKey and you say, hey, I want a voltage regulator that has 5 volts, like the 7805, for example, that's the nominal. That's what's stamped on the package. But in reality, the processes aren't perfect and they have tolerances, and as long as they're within the tolerances, they're good. So that's where this min and max comes into play. It's actually establishing what the tolerances are. So if you're within that range, that's good, but typically you want, there's a word typically, you want to be in a nominal range, okay? So that's what this section's about. Like, they talk about ripple rejection. So ripple rejection, if you remember, was talking about the ripple component of a power supply. Well, we wanted this part to be able to see, okay, there is a ripple voltage, but how does it respond to it? Because that ripple is really, it's noise in the circuit. So if we're trying to regulate at a particular voltage value, and this circuit, like for digital circuits, it really needs to be clean, then that ripple is detrimental to the voltage regulator, and therefore that parameter is going to tell you exactly what the rejection is. So in this case, it's got a frequency of 50 hertz to 10 kilohertz. That's one test condition. The other one is 50 hertz to 10 kilohertz, and it's got a capacitance, and this is the reference capacitance of 5 microfarad. So if I look at the first line, typically is 74 decibels. Now decibels deals with the sound intensity, and with that frequency, that's the rejection for the sound intensity, okay, because we're talking about frequency. So again, this particular power supply or IC could be used in a switching mode application, and that's another discussion. The one that we're focusing on is more linear because the circuit's more, it's not as complex, but it's effective. But if you really want a real nice stable voltage and it's efficient, then you go to switching mode. So this could be used in a switching mode application because again, it's got frequency. You may want to switch this this circuit at that frequency, but it's talking about sound intensity. So that's the limit there, and that's the ripple rejection, because this guy is, AC, and it's putting out noise, and you want to make sure that this device can actually handle the noise. Therefore, the rejection element, or being able to impede it, right? So you got some other values here, like average temperature. That's another important parameter. It's got minus 55 degrees range of temperature it can work in. Okay, so not getting into a lot more details, but this is critical in terms of troubleshooting. If you're swapping parts, you want to make sure that the part you're swapping is equivalent to the actual part. Okay, so that's that guy. Now, here are some typical performance characteristics, and this really comes from that section we looked at that's talking about characteristics. So they plot everything, and as they say, a picture's worth 1,000 words. Well, if I'm designing, these characteristics will come into play. If I'm doing some analysis, like, again, really deep down troubleshooting, I may have to look at some of these curves to see, okay, is that part within the specification related to the specific electrical parameter. You can see here maximum power ratings. That's important too, because we don't want the part to overheat and cause a catastrophic failure. So, and again, these devices, particularly transistors, since they're more current dependent, they can reach a point called thermal runaway. That's when it starts sourcing too much current internally, and it just burns itself out. So these characteristic curves play a role in you kind of getting a cursory look of whatever parameter you're looking at, what is that performance, and then if you're designing, you can actually design based on these curves. Okay, and again, that's they have courses on that you can take. I mean, professional courses, and that's a discussion by itself. Now, this is the last section I'm going to talk about, is application. So one thing that's always important is when you folks take these classes, when you build these circuits, you're learning about the application, like what can this diode be used in terms of something useful. Well, it can be used here as a power supply, right? So you'll see in data sheets they have typical applications. So what they're doing is they're taking a lot of the, say, detailed design aspect away just a little bit, where you can focus on how can I use this in a particular application for your product, okay? So they have different versions of, well, voltage regulators. So they got a basic low voltage regulator. So that's a typical one. And that on this printed circuit board is probably this one right here. Then they have another one, basic voltage regulator. But notice the difference. They're telling you, since this is adjustable, that you can get a voltage of, or out, 2 to 7 volts. So if you need a power supply, like in the case of a, say, digital counter, and 5 volts is appropriate, this will be the one that you want to use, because it's what, 2 to 7. So you can adjust this for 5 volts and you're off to the races. So it gives you a little equation that allows you to determine, but in this case it's got note R3, it's got this equation right here for maximum temperature drift, and they have some other equations right here. So these will allow you to select the voltage that you want, like right here, that's the equation where you want 2 to 7 volts, you use that equation. So basically it's the combination of resistors times the reference. Now this equation right here, this should look pretty familiar, and that is the voltage divide rule, okay? Divider rule, because I got a voltage divider, which is right here, and then I'm going to set, and that's going to allow me to adjust my output voltage, but I need a reference voltage, okay? So with that, I can get the output that I'm looking for, okay? So there's an important equation. And right here it tells you, it shows the figures for the application. So we're looking at 1, and then, not this one, but figure 1 definitely, okay? And then if you look at the other figures, you can use that equation to get the output voltage that you're looking for. Okay, so this section is really, really important because it's about application. So if we look on the next page here, we can get a negative voltage. And depending on the application, maybe you do need negative voltage. Here's a good example. The 74-1 op amp, and the op amp is this, which is an operational amplifier. It has 2 pins on it. It has a positive voltage rail and a negative voltage rail pin, and it also has a ground. Well, in order to operate the 74-1 op amp, it needs a negative supply voltage. So you could probably use this to power up that op amp, okay, because it generates a negative voltage. Here's a positive voltage regulation. So now what you can do is you can have 2 of these. One will provide the negative voltage for that op amp, and the other one will provide the positive voltage for the op amp. And there you go. There's your application, right? You can use it for driving or powering a 74-1 operational amplifier, okay? If you're looking for things dealing with current limiting, there it is. And this power supply, or traditionally all power supplies have current limiting. So what that means is you can adjust the current, sourcing current, and that's important because if you're driving something that's current sensitive, you don't want to exceed the rating of that device, okay? There again, the data sheet. So here we can actually provide a current limiting feature where if it starts to creep up past that limit that you, in this case the load is sourcing, it will actually bring it back to a safe level. Thus it's limiting the current, right? So that's another good application for this IC, okay? Let's see here. So data sheets are a good resource to have, and you should always consult them when you're troubleshooting, designing, or even doing a combination of 2. I consult them a lot when I'm doing my projects, and you learn a lot too because a data sheet has so much information. It is a learning resource. So here's again some other power supply applications that you can use this for. Let's see here. Yeah. Oh, here it is. Positive switching regulator. So remember I was talking about that ripple rejection, and it had kilohertz. With a switching regulator, it's efficient because it's switching the driver, in this case usually is a transistor like a power MOSFET, it's switching it at a high frequency. Therefore, when it does that, it's really managing the current that's flowing through it. So if you imagine, if you took a light switch and you start toggling it real fast, okay, you can get it to, well, when you do that, that's modulation, but you can get it where you can manage the current that's going through the light bulb. So every time you turn it on or off, that means what? The current's being sourced on and off, and that will prevent the filament and an incandescent light bulb to burn out. But if I switch it constantly at a high frequency, therefore that current is going to be at the right level and the filament won't burn out. Okay, so that's a really good application, and most power supplies today are switching regulator power supplies because the efficiency is important. When I talk about efficiency, it's really a relationship between the input power and the output power. Okay, so it's P out divided by P in, and that'll give you a fractional part, and then if you multiply by 100, you get the percentage, which will give you the efficiency. So traditionally, when you use this method of switching, again, you're managing the current, and that's going to keep the thermals low. The efficiency goes up, and typically for switching mode power supplies, you want an efficiency above 90. Okay, if you at 95%, that's good. Definitely 99% is really good. Okay, 100 is golden. But yeah, that's where you can get really good efficiency out of power supply. It won't be heating up, and therefore the longevity of that IC will be very long lasting, and also the device that's driving won't be under the burden of too much current, and therefore it'll be efficient as well. So you're giving it longevity. Okay. And then there's some other applications for power supplies. Here is some information related to if you want to design a printed circuit board. And one cool thing about Tinkercad circuits, if you're not familiar with that, when you breadboard that circuit, and the way it works is, like if I'm going to design a power supply or do a prototype, first thing I'll do is I'll do a breadboard. So I'll lay it out on the breadboard, I'll test it for functionality, and then I want to move it into a fixed design, meaning an actual printed circuit board. Okay? Or you can do point-to-point wiring where it's perforated version of the Solids breadboard, but all the wires are what? Connected point-to-point to the various components. So, printed circuit board. Tinkercad circuits, once you build it on a breadboard, you can actually get the actual geometry of what you created, and that geometry is called it's like a rat's, they call it a rat's nest. So you can move that file. It actually has an export feature where you can actually drag what you've created on the breadboard, and then it'll put it into a file that Fusion 360 can look at, and you can actually Eagle is a CAD package for doing electronic design. It'll actually show you the components, and it'll show the wires connected, and from there you move it on the board, and then you can actually create a printed circuit board. So they added that feature in there, and the reason is because Autodesk is responsible for AutoCAD, Fusion 360, or is it 360 Fusion? I always get reversed, but it's the CAD package where you can do mechanical, electrical designs. You can actually do, I think, modeling of mechanical systems, but you can move it into what I call the electronic design automation world, where you know it works. Now you want to do a permanent version of the design for a circuit board. Once you have that, then you can actually have it manufactured, and now you have your permanent product, right? So something to explore, but that's where this information comes into play. It's got physical dimensions. So it's showing you the various packages of the component, and if you're going to lay out a printed circuit board, this is very, very valuable because it shows like the pins and the spacing. The spacing is known as the pitch. And if you're soldering this, you got to make sure that you don't create any solder bridges. So this section is very important. Here's that dip package that is on that board, and it shows the information, the height, the spacing between the pins. It's got all that good information, and you can use that to lay out your printed circuit board. And that's what they've done here. They actually took this information and they created, in this case, BK, the layout for their board right here. Okay, there's all my papers. Okay.
Yes, all the data sheets, just the
All
entire
the
data.
data sheets. I guess I was upset, you know, because it's like Plank he's something else, right? No, you're not.
Yes, I am.
No, you're not.
You're not.
There you go. Okay, so one more thing, demonstration. So this is the inside. So here's the outside. So let me.
Pick up all the data sheets. We just forgot about a couple of them under there.
So turn it on. Okay, so let me turn it off. Okay.
You want to turn it off?
Well, because I got this light right here.
Yeah.
So that's, yeah, there we go. So now it's off. One thing about power supplies, safety tip. You notice that this was on. We don't want to have this output active, meaning we got voltage being sourced out of the power supply, because someone can inadvertently come by and touch it, and bad things can happen. Okay, so safety practices, always turn it off. And if you're not really using it, for me, especially high voltage circuits, I'm going to pull it from the main source, okay? So now no one will get hurt, okay? So safety. So now I turn this guy on, and you can see here where that LM723 integrated circuit is being coming into play. It's adjustable, okay? So you can see the voltage right here. That's the maximum range. Now, they'll show a nominal value, and this probably is, just by looking at the value, it could be 0 to 30 volts, but again, the tolerances kick in, and you may not get to the high end, like the 30 volts. Sometimes you might, depending on the selection of the components, meaning the passive components. They play a role. You got some semiconductor components that play a role. There's a pass transistor, so this is a series voltage regulator, and that pass transistor is going to help manage the current, okay? Now, also, there is no really, with the exception of this meter, which it shouldn't be, we can get a little higher than that, and there's an adjustment where you can actually increase the current. It should adjust the voltage as well, but that's pretty good, okay, from the standpoint of it does provide the necessary output voltage, okay? So if you need, say, 5 volts for a digital circuit that you're working on in a class, or you're building a digital circuit like a counter or some type of display, maybe it's a potentiometer and it needs a 5-volt source, you can adjust it, right? So you have the flexibility of adjusting it. Let's see if I can get the 5 volts there. It's like a video game. Look at that. Trying to get there.
It's going to get close.
Yeah.
The only thing this power supply doesn't have is a fine-tune button. Because what we're doing right now, you're going to see it a lot on power supply, a device called coarse and fine. What coarse means, you moving it through big numbers, like 5, 6, 10, whatever. The fine goes to those details number, like you're trying to get 5 volts, but you keep getting 5.09. That fine will knock it down to 5.001 or 5.0, something like that. That's what the fine means. You're fine tuning it to get as close or at the voltage or current, wherever number or listing that you're looking for. That's important.
Right, that is very important. And if you notice here how the power supply, it started high and it reached like 5 volts and is dropping now. That could be attributed to the capacitors, because they're charging and discharging. And again, there's no load on here, so it's pretty much open, in terms of the ports here, the banana jack. So it's trying to adjust, and you can see here really that value is 4.989, and it'll just keep changing because the components are heating up a little bit, and they got a little bit of swing value as well. So 4.9, if you're recording, like you're documenting this, that would be, if you say, hey, you round, it's 5 volts. If it's not something critical, that's good. If you're doing like biomedical work, that's very, very critical. So you want the power supply or the components to have a very, when you talk about the tolerance, it needs to be really, really tight, the tolerances. So 5% is typically for standard resistors, capacitors, but if you're doing something that's, like I say, related to healthcare, then it should be, as low as possible, like 0.1%, tight tolerances, right? So that's what we're seeing right here. Current's flowing through, and it's still, components are changing the thermals. It's not like I can't touch it. It's like, whoa, that's hot. But internally, that current's flowing through those components, and it's, as you can see a little bit of drift. So that's probably one of the specs that is on the data sheet, is what's the drift of this output voltage. And you take note of that, and you'll talk to your customer, or if you're replacing a part and you're troubleshooting, you'll make note of that too, okay? Traditionally, for automation systems, it's not that critical. That will be a good value to have. The system will still function properly, but again, if you're doing something that's really critical, again, like biomedical equipment, that's really got to be stable, more stable. So the IC will be has a better specification associated with that tight tolerance. Okay, so that is my discussion for adjustable power supplies. I hope you guys learned some things. And again, I always tell my students, some of you probably have me before, don't let this just be the end all. Like, you take the class and you say, hey, I got the knowledge, and then you take the next class, and then Mr. Kelly or myself or another instructor may give you an assessment, and then that's really going to be a testimony of, do you really know it? This field is so dynamic, therefore you need to always practice the basics. DC, AC fundamentals. If you've taken a basic electronics, which we're talking about right now, you should be taking notes, and then buy a kit. Put things together, because companies are looking for that. It's about what hands-on, right? So if you can do that, you can start to build up, a little lab, and that will help tune your skill. So with that, I'm done. We'll see you guys next semester, and keep on learning.